Okay, so hello and welcome everyone to real-time processing with Apache Flink. My colleague is Gyula Fora, I'm Martin Balashi. We are committers for Flink, a really new Apache project. We just graduated from the Apache incubator in December, and both of us are specializing for streaming. Although this conference around Hadoop is primarily focusing on batch processing, we have already seen this hype about stream processing. People are starting to realize that data is naturally in motion, and data in motion has value that is related to latency. But this field is not as mature as the batch processing field is, and there are a lot of solutions out there. So I would like to quickly give you a walkthrough of the models and the basic concepts that are here in the stream processing space. Then I would like to give you a quick overview of Flink, and then Gyula is going to speak about our concrete solution and our plans for the future. So let's have a look at the stream processing landscape, or more generally, our closer relatives, the guys in the Apache space. One of the standard solutions is Apache Storm with its low latency solutions, and then there is Spark streaming with mini batching, the Samza guys with really powerful abstractions for the stream, namely Kafka, and state monitoring. We would like to give some more emphasis for windowing on a true streaming runtime. Let's touch a bit on the internals. So what does Storm give you on the model level? It gives you the so-called continuous operator model, which means that you have this distributed physical plan, and the operators are long running in there, and your data is flowing through this. When you look at the API level, this means that you have this graph compositional API. They call it a directed acyclic graph. Sometimes you don't have to have this DAG feature. You can actually build cycles in it. When it comes to fault tolerance, Storm gives you at least one processing. They are tracking individual records. When we were assessing Storm, one thing that we realized that maybe the cost tolerance, fault tolerance is a bit more costly because of this record by record basis. So we decided we would like to improve a little bit on that in Flink. We also recognized that serialization can be a bit costly because Storm is not strongly typed, and that this low-level API might not be the most productive for you. Of course, it's really cool that you can control a lot of things, and this graph compositional API is really general, but maybe we can up this a little bit. Let's have another big change and have a look at Spark streaming. The way the Spark guys designed this, they decided to ditch the long-running operators, and they went for a bit more fault-tolerant application in the sense that they already had a really nice fault-tolerant application, namely Spark, and they decided to build a streaming engine on top of a batch engine. How do they do that? Well, you have your streaming data incoming, and then you can do these mini batches, 5-second windows of your data, for example. You configure that before your job, and then it launches batch jobs for these things. It gives you relatively high throughput in comparison with the long-running queries model. At the same time, Spark has a nice higher-level functional API, and because of the batch fault tolerance, it gives you exactly one semantics. What are the downsides of this issue? Well, because if you have this inherently batch runtime, you don't really have a long-running state. For example, when you would like to have some collection or some logic that actually sees all of your data, that you won't really be able to do that in the system. You can do a lot of things, but not particularly that. Another thing that is a bit misleading is windowing in Spark. They tell you that, okay, you have this 5-second windows, and there you can do whatever you want. Exactly when it comes to data-driven windows, where you would like to detect a user session that can be arbitrarily long, this solution might not be the best in performance, and it feels a bit tight here and there. Also, because of batching your data together, you lose in terms of latency. Let's have a look at Apache Samza and their other notion of the stream. I'm quite sure if you are already in the streaming state, you have heard about Kafka, linked-in solution for persistent stream storage. Basically what they do is they give another notion. Let's name a stream to be a collection of partitions where are strongly ordered. So when it comes to fault tolerance, all you have to do is say that, okay, the last message I read from partition 0 is offset 5. And based on that, you can build nice fault-tolerant applications, and you can also manage your state this way. The way the guys do it is practically they push the state updates also to Kafka. So their application is really much based on this concept. Kafka actually persists your data on disk, so this solution leads to relatively higher disk I/O. And they also have this graph compositional API, not the functional one, which of course a lower level abstraction currently. So what does Flink trying to do for you? Well, at first, Flink has, although it's both batch and streaming system, on the runtime level, it is streaming, which gives you, then you don't have to do the micro batching. At the same time, we offer you this rich functional API, and as I have already told, we are focusing on flexible windowing semantics. We have seen that most of the users would love to have exactly once processing guarantees, but they would like to also make sure that their state is persisted as it is persisted in Samza. So those are the key factors right now that we are trying to focus on. The downsides of our system currently, as the size of the state that we can checkpoint is limited at the moment. It has to fit in memory practically, but of course we are working on that. And the job manager high availability is not solved currently. Okay, let's take a step back and let's give you a little bit intro to Flink, what the system generally offers, not just stream processing, but in terms of batch and graph and machine learning as well. So what's the vision of the system? Well, the vision is to provide a use case complete framework to unify batch and stream processing. So the way we would like you to use Flink is to shove in your batch data, your streaming data, and do a lot of analysis on top of that. Implement your processing in Flink. It can be ETL, relational, graph, machine learning, streaming, you name it. And in this talk, we are focusing on streaming, but just after the lunch, we are going to have another talk with Till and Alyosha, who are going to focus on graph processing and machine learning as well in Flink. When it comes to the runtime, the abstraction that Flinks give you is a distributed data flow. So as I've said, we have these long-running queries that are actually pipelined together. And in here, you can also have streaming nodes or batch nodes. Because of the runtime of streaming, Flink is actually streaming. We treat batch as a special case of streaming, not the other way around. And this gives you a lot of flexibility. Let's have also a quick look at the Flink Stack currently. How is the system orchestrated? We have a number of solutions for, So we have a number of solutions for cluster management. You can run it from your IDE. You can run it on Flink's own cluster management, Yarn, Tez, or in embedded mode. Then there is this common runtime layer under the dataset abstraction, which is the data flow for batch, and the data stream, which is for streaming. You have this common layer that actually runs distributedly. Then there is a code path for the batch solutions with a built-in optimizer, the same for streaming but in a different code path. Actually, we have a solution to run your legacy Hadoop MapReduce jobs on top of Flink. And then besides the Java and Scala APIs, there is one for Python, and then libraries for graph processing, some for data frame-like processing, an ICE API, and the machine learning library. As for Flink as a backend, there are solutions for the Google Dataflow system, so you can translate your Google Dataflow jobs to Flink. Currently, the batch is supported, and the streaming one is in the makings. And there is a pending pull request for the Apache Samoa, which is an online machine learning library for streaming jobs. So practically, this should be something similar that the machine learning stuff provides for batch. So with that, I would like to hand it over to Gyula, who is going to touch the streaming parts of Flink.
Thank you. So hello, everyone. I'm going to talk about Flink streaming more in detail. First, I'm going to give you a short overview of the API. What can you do with that? And then using actually a nice use case to highlight some nice API features. And then I'm going to talk a little bit about fault tolerance and performance and our roadmap. OK, so let's see. So the streaming API has 3 main components: data stream sources, data stream transformations, what you can do on your streams, and data stream outputs. Sources defines outside word connections where you can actually ingest data from. We provide a wide variety of pre-implemented source functionality, ranging from file system sources to message queues like Kafka, RabbitMQ. But we actually provide a very simple interface for implementing your arbitrary source functionality. So you can use that to play around, generate some streams, or whatever you want. As for stream transformations, as Martin has already said, we provide a high-level functional API. If you've seen Spark streaming or any high-level framework, you must be familiar with the transformations we're providing. We, of course, provide a set of basic transformations that you can apply on data streams, like map, reduce, filter, and different aggregations. We also provide some streaming-specific operators, which come from the fact that the runtime is a true streaming layer. For instance, binary stream transformations allow you to share operator state between transformations on more than one stream at the same time. These come in handy when you try to implement things like stream joins. We will see more on this in the use case. A large part of the streaming API, and we're especially proud of this, is the nice windowing semantics that we provide. We do something called policy-based windowing, which lets you define the window size and the slide size independently from each other in very ad hoc ways. We also provide some other nice transformations. I'm not going to go into details. There's absolutely no time for that. You can check our streaming guide for more information about the operators. As for the stream outputs, it's closely related to the sources. Then again, you can connect to message queues, whatever, write it to files, or implement your own functionality. OK, so let's look at the simple use case and see what the API can do for you. So here, we would like to do some financial analytics on data streams. We came up with this example because I think it can be used to highlight most of the nice features that Flink can offer to you. What we're going to do here is read our stock market data. Precisely, we're going to read simple stock symbols and the prices associated with them. So it's not going to be more very financial stuff, but we're going to read it from multiple different sources, and we're actually going to take these streams and put them together in our stock stream, which is going to give a union of our streams. Then on this stock stream, we will do some analytics. We're going to do window aggregations, like computing statistics over our stock data based on a sliding window. We're also going to show you how to do data-driven windows in Flink streaming, and we're going to use this to provide price warnings for larger price fluctuations. And then we're going to combine this with sentiment analysis. We're going to analyze Twitter streams, and at the end, combine all these together to gain some more insight how the stock market and Twitter is related to each other. Yeah, there is a blog post on this example. So if you want to try this out, see the full code, you can go there and check it in detail. Okay, so the upcoming slides are gonna look like this. It's a lot of information, but it's not too complicated. So in the top, we see the visualization of the topology that we're trying to do here, trying to run here. There we provide some basic like data, so you can imagine what's flowing through the topology, and then under that there's the code, and we have numbers to relate the specific parts of the code to the figure. So in the first part, we want to read our sources. So where does your stock data, where is it coming from? I mean, maybe you want to read some part of it from Yahoo Finance, or you have some custom stock source. So in order to read it from multiple places, we can just define a source for each of our stock sources. To do this, we will create an execution environment which represents the context in our programming language. So in this case, Scala. And we will use this environment and add some data streams to it. So as the first step, we will create a socket, a text stream. Basically, it will receive a text input from a WebSocket. And we will parse this information into our Scala case class. And then we will do the analysis on that later. In the third step, we generate some stock data using this generator that we implemented. You can find the details on the blog post. It just shows that you can actually write some Scala function to generate your data, so you can experiment with that. And in step 4, we're just going to take our first stream and merge all the other streams into it, which will create a union of the streams. So now we have our stock stream. Okay, so now it's time to do some analytics on our stream. So one common example is that people who work in this field, they do sliding window averages on the stocks. I mean, of course, it's not very useful to look at each price information like one by one. They usually take a window. In this case, we took a window of 10 seconds, and we slide it every 5 seconds, and we want to compute some statistics over it, like maximum price or average price for a specific stock. To this in Flink, we will define a window in our data stream. So to do that, we take our stock stream, and we call the window method on it, which will give us a window of 10 seconds. And we will actually call every time of 5 seconds, which will make this 10-second window slide at every 5 seconds and compute our aggregations on that. One thing to note here is that you can see that windowing that we added here is not predefined in any way when we created the topology. So we don't have to define the granularity of our windowing or nothing. I mean, windowing in Flink is just another operator that creates an arbitrary discretization over the stream. In this case, we used time windows, but this could have been count of 100 elements or any other user-defined function to actually define the window size. Now that we have our window data stream, you can think about the window stream similarly as a stream in Spark. It has windows, and we will apply transformations to them, and it's going to output one or more elements per window. So it's really just discretization on the stream. So in this case, we're going to calculate the lowest price in that window in general, or we can do we can also group by the symbol inside the window and compute the maximum price per stock, or we can actually take and map the window and compute the mean. Here, the map window function might be a little tricky for first. It just basically says that we pass the content of the whole window into a function. Yeah. So what else do we want to do on this? So it might be interesting from financial analysts to detect like fast price fluctuations and maybe output some warnings or send emails to the clients that something is happening, something's going on. So to do this, we will once again use our flexible windowing semantics to define windows. But now, instead of defining it in terms of time, we will define it in terms of price change. So each window will contain data which are from the beginning of the window. They're less than 5% price change away from the first element. I mean, if you've programmed in any other streaming systems, this is actually a very tricky problem to implement it. So, but we provide nice functions to define these high-level functions. So in this case, we define our delta window. Delta just means that you define your custom distance function between the first element in the window and the last element. And here, we're not going to do anything with the elements of the window. You can imagine doing some stuff with that. But here, we're just going to output some warnings. So what we're going to do next is, let's say we want to collect and count how many times, how fluctuating a stock was in the last 30 seconds. So we're going to take a window of 30 seconds and just count all the price warnings for a specific stock. Okay. So now let's go somewhere else. Let's read a Twitter stream. So in this case, we generate tweets. We provide a connector to Twitter. You could use that. But just for the sake of this example, we just generate some tweets. And then we want to do some sentiment analysis. I mean, this is going to be a really basic example. What we're just going to do is extract the number of times the stocks were mentioned in the Twitter streams. So basically, we were going to read the tweet stream, filter out our the symbols of interest, and after that, for every 30 seconds, we're just going to do a sliding window word count on these stock mentions. So if you see where we're going here, now we have the number of price warnings every 30 seconds for a specific stock, and also a number of times the stock was mentioned on Twitter. So now we can actually take these two streams and combine them in a clever way to get some more insight about how this market works. Maybe there is some correlation between the Twitter stream and the stock data. So let's take a look at that. So in order to do this, we actually need to somehow join these two data sets, or data streams, right? And we need to join them at the same time. So what we're going to do here, we're going to do something like called a window join or a temporal join. It is basically an equijoin on time windows. So we take our warnings per stock for the last 30 seconds and join it with our tweets per stock for the number of mentions for the last 30 seconds on a window of 30 seconds where the symbols are equal. So we're going to join on the symbol. And then we're just going to output a tuple 2 containing the number of price warnings for this stock and the number of tweet mentions. And with this stream, we can do whatever we want. We can compute correlation. In this example, we just computed simple correlation. Then again, most of the code you cannot see here, like for instance, the compute correlation function, that is a user-defined function. You can check the blog post for more detail on that. OK, so that was the use case. What about fault tolerance? So Martin has already said that we're going to provide exactly once processing semantics with user state checkpointing. So it's actually exactly once processing semantics with also with respect to user state updates. So in order to do this, we've developed our own algorithm for distributed snapshotting. Our algorithm is a slightly modified version of the Shandy-Lamport algorithm, if you're familiar with that one. I don't want to go into too much technical details here. It's quite complicated. If you're interested, we can explain it in detail after the talk. Just come to us. But in general, what's happening here is that from the job manager, the master node, we send checkpoint barriers to the sources, and they will push these barriers as markers through the topology and snapshot the state at each operator. And the numbers there can actually show you like the order in which these operator states are going to be checkpointed. Okay. Performance. Since we provide a high-level API, this allows us to make some nice performance optimizations for the streaming programs to provide a very nice out-of-the-box performance. We haven't seen it in the Scala API, but if I'd shown you a Java example, we would see that streaming topologies are strongly typed. So we can actually use this to have some quite elaborate type extraction before we actually submit the topology. And we can use very efficient serialization in the runtime. Also, we use different optimization techniques like operator chaining. If we figure out that we're not going to shuffle the data between two transformations, we can actually like collocate these and totally avoid serialization. This can actually win you a lot. And there's also different query optimization techniques we use for windowing commutations and so forth. I mean, if you want to hear more details, talk to us, check the website, and whatever. This actually wins us a very competitive performance instead of a number of records processed. Our latest benchmarks that we made showed that we can actually process 1.5 million events per second per core. To put this into context, Storm promises 1 million tuples per second per node. Yeah. I mean, that's not that simple. I mean, we couldn't. It's hard to get that performance from Storm, actually. I mean, and also anyone who can help us to do some nice benchmarks, who are like a Storm expert, we would take some help to fine-tune Storm to make a nice benchmark, so we can compare these nicely. So yeah, then talk to us if you have some good ideas on this. Okay, regarding our roadmap. Currently, we're working very hard to provide a high-throughput, persistent state backend for the operator state. As we said, currently we're sending stuff around in Akka, but we're looking at different in-memory solutions for state management. Also, as Martin has already mentioned, job manager high availability is currently an issue, but we're working hard to fix this as soon as possible. We're also actively developing application libraries on top of streaming. We want to extend the aggregation capabilities to provide more possibilities to compute general statistics over data streams. We want to have a nice pattern matching library. As we said, since it's a true streaming runtime, we can do anything that you could do in systems like Storm or any like complex event processing systems. We're also working on a machine learning library. This is related to the Samoa project, but we actually want to combine the machine learning done in batch and streaming. The model that we are developing there is related and probably will remind you to scikit-learn. So we're going into those directions. We're also developing a graph processing library for streaming. That is actually a very exciting topic. And Vazia is here, who is like one of the main guys behind this thing. It's super cool. We're also providing integrations with other frameworks. We're working to integrate Flink with Zeppelin. You probably know this project very well. It's a cool notebook tool for big data frameworks. And as Martin has said, we have a pending pull request for a Flink adapter for Samoa. Yeah. So with this, I'm going to give the word back to Martin to wrap things up. Thank you.
So as for a summary, Flink in general is shooting for to be a use case complete framework for batch and stream processing. At the runtime layer, we don't distinguish between those two kind of jobs, and it's a true streaming runtime. As for streaming, we are optimizing for flexible, data-driven windowing semantics, and we provide a competitive performance. And I also have to highlight that we are just getting started. The community is ever growing. We have around 100 contributors. And in autumn, Flink is going to see its first dedicated conference. So if you are interested, please join us in autumn in Berlin. Thank you very much. We have around 10 minutes for questions. Yes, please.
Can you do the join of the streams on count-based windows as well? Like a zip in Scala, for instance?
Well, in the current version, it's only allowed for time windows. In the next version, we're actually going to rework this window join to use the same trigger eviction method. I mean, actually, zipping the two streams is super tricky because zipping is a blocking operation necessarily. And I mean, we're probably not going to implement something like zipping. This is extremely dangerous to the application. It's probably going to blow up at some point.
And it also brings in a lot of latency. So what another design that you can do is you build up this eviction thing, the window of one stream that you keep in memory, which shouldn't be, of course, really big. We are doing streaming. And you, when the other tuple comes up in the other stream, then you know that, OK, this guy is going to need that window from the other one. And that's a bit different and much closer to the current general windowing semantics.
OK, here we have a question.
Related to your persistent state, so for your exactly one semantics, I assume your performance numbers was with the persistent state enabled, right?
Actually, the performance numbers that we shown were both for Storm and for Flink without persistence. So it was just streaming through a lot of data. It was more about the throughput of, if you wish, the serialization and the network stack and those kind of things, and not with enabled persistence. It's really tricky because then you would need to have actually not just Storm, but Trident if you want to compare exactly one semantics. So then you have to actually distinguish really well. I'm trying really hard to actually have eventually a nice performance blog post out, but more and more I see that it's really tricky, and little things can mean a lot if you configure serialization correctly, if you configure your network buffers correctly, those can mean a lot.
But actually, I think the runtime overhead of our algorithm is pretty slow. I mean, just broadcasting the barriers through the topology are basically costless, and the state snapshots are happening asynchronously. So, I mean, compared to what Storm has by record-based acknowledgements, I mean, this is practically zero.
And is your state sharing you showed the state manager? Yes. Is that a single central one, and how does that scale? Are you planning to make it more decentralized implementation?
So what you saw there, the state manager, I mean that's the work in progress, the state backend. I mean currently it's centralized in the job manager at the master node. At one point we'll probably have a distributed in-memory database or something like that. So it's going to be centralized.
Okay.
Yeah. Any other questions?
On these window aggregations you do, do you also work on a sliding window fashion, like when an update comes into this 10 seconds window or one leaves, you generate another result?
You can actually do that. So if you do a, you can do eviction like, let's have it, thank you. Yeah. So basically what you can do, if you configure it like trigger every element, then that's basically what it does. So these are independent things from each other. You can have a window of 10 seconds every count of 1. So then it doesn't have to be both time or it's up to you.
Yeah, but if you're referring to the something like the slider presentation where they do incremental window compression, yeah. So that's actually happening under the hood as an optimization. So in this case, what the optimizer layer does is it detects that you have a sliding window of 10 seconds. So they're both the same unit of measurement. So we actually know that, okay, now we can take 5-second chunks and only compute those, and we incrementally update them. And we don't recompute the whole window. We do as much as we can to do the same optimizations as, for instance, slider does.
So you use also associative operations to do
that? Yeah, exactly. So we minimize the memory overhead. So whenever it's possible, we never keep the whole window in memory. We start reducing, so we only keep probably like a few elements depending on the bucket sizes.
Okay, thank you.
What kind of tools do you provide, or are you planning to provide to install, configure, and manage Apache Flink?
Okay. You want to take it, or should I take that?
Go ahead.
Okay. So, I mean, currently we have some scripts to set them up in different cluster environments. There's this project called Caramel. I'm not sure if you've heard about it. We're planning to add some scripts to deploy Flink automatically to EC2. But we have some scripts to deploy to Google Compute Engine. So if you want to try it out, you should write to us, and it should be very easy to set up for you.
Yeah, and there's also some work with Cloudera to integrate Flink with the Cloudera manager. They won't put it right now to the Cloudera distro, but it will be a tool to actually where you can do it yourself. If you have a Cloudera distro, you just run a script, and then Flink is also in there for you.
Okay, so there was another question in the back. Yeah.
Hello, you were saying about in-memory database management, state storage. Have you already evaluated some, or you have in mind what you could use for that?
I don't want to say specific project names because it's really we're in the beginning of figuring something out. But the main point here is that we want to have something where we can actually do state delta updates. So what the Samza guys do with Kafka, so they incrementally checkpoint their state. That's a very good idea, and we would like to we take that from them, and we do something similar. Maybe not using Kafka, but we would like to definitely use some open source solution that allows in-place updates using delta functions or something. That would be the final goal. Yeah.
All right. And this second one may be a little bit stupid question. This framework, I mean the Flink, right, and this streaming part at runtime does not necessarily, for instance, rely or must not necessarily touch HDFS.
You can actually touch it. So because of Flink in general has a batch solution as well, we have sources from HDFS, and you can write to HDFS. Just of course, if you would like to have a streaming solution with high throughput, low latency, then it's pretty much not recommended to touch this.
But in general, it's totally independent. So I mean, so your job, even your batch or streaming job might run completely independent of Yarn or HDFS, whatever. It has nothing to do with that.
All right, thanks. That was my question.
Any other questions? We have 46 seconds. I can take a quick one.
Okay, if no, then thank you very much.
Thank you very much.